Yes, yes, please go ahead.
Okay. Was it visible though?
Yeah, it was visible, but it's gone now.
Oh, okay. Alright, so we are going to speak about t-tests today and this very cliched intro slide that I've given. And before we start, I'd just like to mention like I was speaking to Munna and Pooja already about this. I very recently learned, like, as in this topic was taught to us in college very recently, and I am not very confident and sure about it. So I took this up as a challenge to present this today. So, what would really help me is if there could be some form of interaction. So, here and there, I would ask you to come up with hypotheses and, just, help me out with interacting a bit. And I do not think I'll be able to see if someone sends a chat or raises a hand or anything. So, Pooja, could you help me out with that?
Yeah, yeah, yeah. We will let you know if there's any
Okay,
chat.
okay, okay. So, probability is the first thing we need to speak about. So, ultimately, this is a portion from a book. The reference has been given on top. So, ultimately, our goal is to draw inferences about relationships in the population, right? So, it is not really possible to statistically treat the entire population. Therefore, we resort to samples. But then it is also, it cannot be said with ultimate certainty that the sample values and whatever comes as a result by treating the sample statistically, it cannot be proven that it will hold good even for the population. So there is always some level of uncertainty that is associated with um, anything that we do in behavioral science research. So I was actually about to name the slide what are the odds, but then I realized that odds, chances, and probability, these three terminologies, they are spoken about very interchangeably, but in statistics the three of them are different from one another. So here is the difference. Like odds are expressed as fractions, as in it's given here. The odds of winning are like 1 and 2, whereas chance is expressed as a percentage and probability is expressed as a decimal. So here in this kind of uh, t-tests and other inferential statistics, we generally speak about, we compute the probability. So I would try my best to hold on to this term probability. So this is the guy William Seeley Gossett who came up with the t-test. And like there's a very interesting history to how it came about. The guy who made tea for his brewery, pun intended. But yeah, so we'll watch a video on this.
The audio of the video is not audible actually.
It's not audible.
No.
Yeah.
Okay, so how do I do it? Is it on Meet?
I think when you share your screen, there is an option where you can tick share audio as well. I'm not sure if that's how it works everywhere. Can you like unshare your screen and then reshare?
Yeah, I'll do that.
Below somewhere you should find the option to share audio as well.
Is it okay now?
The video is not played yet, right? You
I
have not
shared
clicked
it.
it.
Okay, let me see.
You have not.
Yeah, right. Okay, hold on for a minute, please. Bear with me.
No worries. Take it.
Okay, I'm playing it. Please let me know if it's audible.
The t-test was developed by William Seeley Gossett. He worked at the
Yes, it is
Guinness
audible.
Alright.
Brewery over 100 years ago, and he developed this test to determine things like the difference between barley yield. Now, he wanted to publish this statistical test to share it with other statisticians, but the brewery was nervous. They didn't want him to publish. They didn't want him to give away any secrets. He finally convinced them, but he had to publish under the pseudonym Student. So instead of this being known as the Gossett's t-test, it's known as the... So in this video, I'm going to start by conceptually showing you what the t-test is. I'll then show you how to calculate the t-value, run a t-test, and then finally, how to do a t-test in just a few seconds using a spreadsheet. So imagine I have two fields of barley, field 1 and field 2, and I want to compare them, but I don't want to cut down the whole field. I just want to do some samples. Samples from 1, samples from 2. So I could get a sample from field 1. Now, it won't be a perfect normal distribution like this. It's going to be more of a histogram that looks like that. And then I'm going to get a sample from field 2. Now, which one of these has a higher yield? Well, we could figure out the mean. We could figure out the average of each of those samples, and it looks like the average in field 2 is higher than the average in field 1. But that's only part of the picture. The mean only tells us so much, because we could have different distributions, and depending on that distribution or the variance within that sample, there could be a statistically significant difference between the two or not. And that's where the t-value comes in handy. It's really a ratio of signal to noise. Signal is going to be number numbers that tell me the difference between these two samples, and noise is going to be numbers that kind of get in the way. So how do I figure out the signal? Well, the easiest way to do that is simply find the difference between the two means. And so if I calculate the mean in sample 1, we'll call that x bar 1, and x bar 2, the absolute value or the difference between the two, is going to tell you how much signal there is, how much difference there is. Now, how do we get at the noise? That's going to be in the variability of the groups themselves. And so the factor is going to look something like this. What is S1? That's the standard deviation. Remember, that's how far our data is spread from the mean. But we're not only taking the standard deviation, we're actually squaring that. That gives us something called the variance. And so if I increase the variance, that's going to lower my value. It's like giving me more noise. Now, the other factor in here is going to be the number of samples that I'm taking. As I increase the number of samples, that will actually increase the signal up to a point. And so again, the difference between the means is going to give us more signal, higher t-value, and increasing that variability is actually going to decrease it. So let me show you how to calculate that t-value. I'm using Excel, but you could use Google Sheets or even your TI calculator. So if you look at these two samples from field 1 and field 2, can you tell which one has a higher yield? It's really hard just looking at it. Is there a difference between the two, and how much is that difference? So we'll use the t-value to calculate that. First thing we have to figure out is the mean. So in a spreadsheet, you hit equals average instead of mean. I'm going to put left parentheses, and now I'm going to select that entire sample set from field 1. End parentheses, and then I'm going to get a mean of 15.38. Now I can select that and drag over, and now I get a mean of 15.68 in field 2. Next thing I have to figure out is my standard deviation, so that's equals STDEV, left parentheses. I'm now going to sample that field 1. And now I put end parentheses, so we're going to have a standard deviation of 0.3124. I'm now going to apply that into field 2's data set, so we have a higher standard deviation. Remember, I now have to calculate the variance. To do that, you have to square the standard deviation. So I'm going to select that cell and bring it to the second power. So there's my variance for field 1, and now here's my variance for field 2. And then finally, I have to know how much data I'm actually collecting. So if you hit equals count, that'll count the number of data. And so I'm going to count those, and we get 16. So we got 16, and then it's going to be 16 in the next one as well. Now you could use a spreadsheet to calculate this. You could do it by hand. It takes a long time to figure out standard deviation by hand, so I'd encourage you to use something like a spreadsheet. Now I have all these values. I'm simply going to plug it into my t-value like that. So we've got the signal on the top, so I'm going to find the difference between these two, and then I'm going to figure out my noise on the bottom. Remember, you have to divide this, add it, and then take the square root of that. So if I do the work for you, we've got a signal of 0.30, a noise of 0.13, so I've got a t-value of 2.3. What does that mean? Since it's higher than 1, that means there's more signal, there is noise. So I'm going to put that over here to the side, because this video is not about the student's t-value, it's about the student's t-test. So now we're going to run a t-test. What are we testing? We're testing our null hypothesis. Just like we do in a chi-squared test, what we're going to start with is a null hypothesis that says there's no statistically significant difference between the samples. In other words, any difference that we would find is simply due to chance. You then identify a critical value, a number. If our t-value is lower than that, then we don't reject our null hypothesis. But if we get a t-value that's higher than the critical value, then we reject our null hypothesis. There must be an alternate hypothesis. There could be something going on between these two fields. Now, how do we find that critical value? We'll use a t-table that looks like this. It looks confusing, but it's really not that bad. So this would be for a two-tail test, and I'll show you what that means in just a second. First thing you have to know is what probability are we going to use. Generally in science, we'll use the 0.05 probability. So that's going to be this column right here. What does that mean? Well, this is an inferential statistic. It means if we were to do this sample 100 times, 95 of the times we would reject the null hypothesis, and only 5% we wouldn't. And so it has a lot to do with chance. So I'm going to use that 0.05. Now we have to figure out what row we're going to do. And to do that, we have to know how many samples we collected and figure out the degrees of freedom. So the degrees of freedom is going to be the samples of N1 and N2 minus 2. So since we took 16 from each, it's going to be 32 minus 2, or 30 degrees of freedom. So here's our critical value. Our critical value is going to be 2.04. So is our t-value higher than that? So this is where we're doing the actual t-test. Are we higher than 2.04? We are. And so what does that mean? We're going to reject our null hypothesis. That means there is something statistically significant between these two sample sets. Now it's not much higher than that. Remember, it's just 2.3. And if we were to look over here to the 0.025 probability, we can see that we're actually lower than that. So we're not positive, but we're pretty sure that there's something statistically significant between these two. Now that was a lot of work. We had to calculate our variance, our means, our sample size, and then find this table. The nice thing about a spreadsheet is it can calculate a t-test very quickly. So what I'm going to do is put t-test here, and then I'll just write in this next cell equals t-test. So there are 4 things I have to put in for a t-test. The first one is going to be my sample set, we'll say from field 1, so I'm going to select that. Then I put a comma in. Now I'm going to grab my data set from field 2. And then I'm going to put another comma. We're doing a two-tailed test, and this is an independent test. I'll show you what that is in just a second. But you can see in just a few seconds we've calculated my probability, or my p-value. What is it? It is 0.026. What does that mean? It's slightly above 0.025 and somewhere in between 0.05 and 0.025. What does that mean? In just a few seconds, we're able to realize that we need to reject that null hypothesis. So it's really simple in a spreadsheet to do a t-test very quickly. Now we did an independent t-test, or an unpaired sample. What does that mean? We had 2 different fields that we were comparing. So you could be comparing, for example, 2 different populations. You can also run a paired t-test, and you would have to select that when you're running the t-test. What would that be? It's if we're sampling the same population twice. So maybe we're looking at field 2, but then we're applying a chemical and looking at it again. That would be a paired test. We're also doing a two-tailed test. And so when we're figuring out that probability of 0.05, you can think of it like this. This is the 0.95 that we would reject the null hypothesis. And that 0.05 is actually split between the 2 tails, because we're not sure which direction that variance is going to be. You could also run a one-tailed test if you're sure of the directionality, but you have to be cautious when you're running that. There are a few assumptions you have to have when you're running a t-test. Number 1, we should have a normal distribution in both the population and in the sample, but it works really well with a small sample size. We also should have similar variance in each of those samples. And then when we're looking at the data points, we should have roughly the same number of data points on either sample. And then finally, this works good with low numbers, but you generally want to be in the 20 to 30 range when we're looking for samples. If we go much higher than that, instead of using a t-test, we'd actually use a z-test. So did you learn everything I showed you? Well, now's a chance to practice it. I've got a sample set over on the left side. Imagine we have 2 plants from population A and B. And let's say we're looking at the leaves that each of those plants have. Is there a statistical difference between those in plant A and plant B? So you should run a t-test. I'll put a link to an Excel file down below. And then once
Alright, so like now that we've watched this video, we do have some idea about what the t-test is, but then we have come across some terminologies. Alright, could I request few people to switch on their videos, please? It would be really helpful because the silence is a bit dreadful, so thank you. Okay, so now that we've seen this video, it was quite like a summary, but then we have come across some terminologies like degrees of freedom, independent and paired t-tests, and one-tailed and two-tailed tests, and all of that. So if I'm going to present the PPT now. Okay, so in short, we can say that t-tests are statistical tests that are used to determine whether there is a significant difference between the means of two groups or samples. So, here, when we say significant, one very common confusion that a lot of us experienced in our class at least, and I've heard a lot of other people too. Uh, Significance here doesn't necessarily have to mean importance, as in we use colloquially. Uh, Even if, say, in two sample means, even if the difference comes out to be significant, it might not be important. So, here significance is just a statistical term, and t tests can be performed on both small and large samples. We can use different other different statistical tools for larger samples. T tests, I think, are mostly used for smaller samples, that is in less than 30. Does anyone have any input here?
Just appreciation, not really input. Just really liked all the slides and video you have put together.
I'm kind of, I don't know, I do not like it. Thank
It's
you.
so good. It's so good. You're doing great. Yeah.
Thank you. So t-tests can be performed on smaller samples as well as larger samples. So another thing that is mentioned on the uses of t-tests is why it differs from z-tests. So can anyone here like volunteer, and if you know why, could you like share why z-tests are not really used, and instead how are like t-tests more advantageous than z-tests? Okay, so I'm assuming there's no one, so I'll just go on. uh, from whatever I have understood, z-tests are, it can be applicable only as long as the sample size is fairly large enough. So what Gossett did, he made this t-test distribution, whatever. He made this to calculate stuff about his barley, and where there isn't a large sample as such. So when we have to manage with smaller samples, we use t-tests.
This reminds me that I'm so sorry I didn't raise my
Thank you.
hand.
Thank you so much.
This just reminds me that in all the papers I have read so far, I have rarely come across like most of the people do t-test, and which explains this, that the sample size thing, it's usually small. So
Yeah. And also because I think t-test is a very versatile instrument, because it can also be used for samples that are larger than 30, right? Because like I've seen a lot of papers use t-test even if they have good enough samples.
yeah, yeah. I think most of the lower threshold is 30, right?
Yeah,
Yeah, so I think most people who have about 30, I have seen mostly t-test.
yeah,
So yeah.
that. And also we have a practical on Likert scale this semester. So there we had to, our sample size wasn't really small. I have to actually read up on that. But then what we did was that we took the upper 25% and the lower 25% of the entire distribution. So that amounted to, it was an independent distribution, and that amounted to 8 observations in each sample. So there, since the sample size is small, we used a t-test. So likewise, t-tests can be, like, these are some use purposes of t-test and how and where they are used. It can be used to compare means, to test hypotheses, uh, for assessing treatment effects. So it can be used in intervention procedures and analyzing experimental data. So these are some types of t-tests. Independent and dependent t-tests are classifications based on the nature of the sample. So in case of independent t-test, what happens is there are two distinct and different sets of samples. So this is where I would like you to interact a bit. Can we come up with some hypotheses, interesting ones?
For independent,
Yeah, like any hypothesis with like two variables, because that is all I know, two variables. All right, so should I move on?
I think people are you all typing? Does anyone?
Oh,
Yeah,
okay, thank you.
yeah. Y'all can also unmute and say it. So because I don't think Anupa can see the chat, so
Yeah, I mean, nothing has to be correct. Even the presentation that I'm doing right now, I do not think it entirely is correct. So,
Irisha, can you please take the microphone closer because it's very low, the volume.
yeah,
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 yeah.
much better.
Okay. So could you repeat again? Are these? It's kind of funny. Is it supposed to be funny? Female students.
So, is this a hypothesis or is this a question you want to study with like a t-test?
So, like, would you like? Okay. So, would you like to compare with like males? Okay. So, like, two like uh what are the two variables between which we are trying to establish a relationship? This is kind of funny because the highest I've got in math so far is 70.
Yep, math was never my strongest.
Anyway, so
I just have like what Irisha wants to study. I think she has
Mhm.
more of a question here. I think this can be studied in terms of like her question is, are score of female students greater than 70% for math? So I don't think exactly t-test would be appropriate here. For t-test we require to compare two groups, right? So
Yeah, like we are trying to measure the difference between two sample means or two group means, simply put. So,
so I
Um,
yeah, please go ahead, Devanshan.
so, in previous semester we did a practical in which we applied the t-test. So we can take that hypothesis. For example, like we compared the job satisfaction level of the upper socioeconomic strata people and middle socioeconomic strata people. So we formulated the hypothesis that the H naught was that there is no significant difference
mhm.
between the job satisfaction levels of higher economic people and the middle economic people, based on like salary ranges or salary brackets. Okay, so this was our H naught, and the H one or a alternative was that there is a significant difference, and then we tested like on whose was higher through the means, like comparing the means of like both the sample groups.
Yeah. Yeah, that so this is thank you so much, Devanshi. So, and thank you so much, Arisha, too. I really liked your question. uh so what Devanshi said right now, this is an example of an independent t-test where our two groups are high, correct me if I'm mistaken again, higher income groups and middle income groups, right?
Yes, yes.
Okay. So since these are two different separate groups, so we have to use an independent t-test here, because these, again, like reiterating, these are two separate groups and one group doesn't have to do anything with with the other group. So here one group consists of one group or sample consists of one set of individuals, and the other group does not have the same set of individuals. So, as the term suggests in itself, they are independent to one another, right? So, here we are using an independent t-test. I haven't really put the formulas here in this PPT because it would have scared me. But then, like, we did see in the video one method of calculating an independent t-test. So, there are like, if I have understood correctly, again, there are like two, three methods of conducting an independent t-test, but then there is one basic formula. So here again, we come to the concept of degrees of freedom. Degrees of freedom is basically how much we can allow the standard error. So for an independent t-test, again, Devanshi, did you have the same sample size for both the groups?
Yes, they were 30.
Okay, so in this case, this is a small uh, equal size sample. So here 30 30. So in this case, the degrees of freedom would be like, ideally the degrees of freedom formula is n1 plus n2 minus 2. So one from n1 we can eliminate and one from n2 we can eliminate. But here, since n1 equals to n2, so it naturally becomes 2n minus 1. So 30, 30, 60, 58, right? 58 is the DF.
Right.
Yeah. No, I am not sure about these simple calculations too. So, like, I was about to just check on my calculator. So, so with each degree of freedom, there is a critical table value, and that critical table value consists of the levels of significance or alpha values that we call. So, um, we generally take the 0.05 level and the 0.01 level. 0.05 level, can anyone volunteer and like share what 0.05 level signifies?
Are you all typing? I think it would be better if people unmute and talk instead of chat. Yeah, Devanshi, please.
From what I think, like 0.05 is the 5% of like out of 95% times, um, the null hypothesis will be rejected. Like it will not be true.
Mm-hmm.
So if it is not true, that means there is no if we are rejecting that there will be no difference, then we are accepting that
Right,
there will be difference
right,
95% of times.
right,
So we will accept the alternate hypothesis. And if
right.
we say 0.01%, it we are then more precise that there
Hmm.
like 99% of time the alternate hypothesis which we are taking, that there will be a difference, will be accepted, and 1% of time there will be a chance that there will be no difference between
Right,
samples that we are taking, or any
right.
uh, relationship that we're establishing.
Yeah, absolutely. I think that's correct, right?
Yeah, also I wanted to add that a lot of times in our TYBA, we are constantly just taught that p value basically tells you like probability of error or something. But I think recently I have seen like a more fitting definition. So the p value tells you the probability of basically finding the value that you got for the difference if the null hypothesis was true.
True.
Yeah, so which means if the p value is very less, that means the probability of it be like getting that value is very less, which is why we reject it and then we accept the alternative.
Right. So when the p value, as in our computed t value, when that is lower than the critical value at 0.05 and 0.01 level, do we accept or reject it? Reject the null hypothesis? We accept the null hypothesis then, right? When the p value is lower than the critical values for t.
I think um, we like accept the null hypothesis when p value, when the calculated p value is greater than p value,
Right. So,
because we
okay.
say that uh, जो हमारा लाइक रिजल्ट है इट इज़ ग्रेटर देन, उसके चांसेस 0.05 से ज़्यादा है, तो यानी डिफरेंस ना रहने के चांसेस ज़्यादा हैं देन कोई डिफरेंस आने से. So we accept the null hypothesis.
Okay. So like we accept it when p value is greater than alpha.
When p, I think Devanshi is saying when the p value is greater than our significance level 0.05, you
Yeah,
accept the null hypothesis, like there is no
no
difference.
difference.
And when it's less than 0.05, there is a significant differences between the group.
Right, right. Yeah. So basically, the slide that I skipped to. Okay, so I just realized I skipped a lot. So again, like null hypothesis, we know by now it is the hypothesis. The way I like to remember is that whatever the question is, null hypothesis just says, kind of nullifies the relationship. So, and the observations are like purely a result of chance. But then, in case of alternative hypothesis, uh, there is a significant difference between the two variables that we are trying to test. So again, like we did come across some hypothesis. The test. So these are some steps for testing the hypothesis. First, we identify a statistic that will assess the evidence against the null hypothesis. So here in this case, since we are discussing T, oh, also I forgot to mention about the one-tailed and two-tailed tests. In case of one-tailed tests, again, how I like to remember, very simply put, is that one-tailed tests are directional in nature. So, for example, if the hypothesis that Devanshi suggested, uh, so if the question was something like, is the job satisfaction significantly higher in the higher income groups uh, rather than the middle income groups? So here these two words significantly higher. In case of one-tailed tests, here we know the direction. Higher is the direction, higher or lower, or anything that also, and if in the question we say in addition to the magnitude, like in addition to just asking us whether there is a significant difference between two variables, if there's also like a degree or a direction that's provided, we do a one-tailed t-test. But in case of two-tailed t-tests, it is just trying to find out if there is any difference between the two samples at all. So again, talking about p-value, uh, p-value is our probability. So when we say that, when we talk about p-values, how we write it, like how we are learning it right now, is the probability p of h not being true, which uh, someone, Pooja, did you like speak about this sometime back?
Yeah, I just said like it basically tells you how likely it would you would find that value you got if the null hypothesis was true, assuming
Yeah,
it is true.
yeah, that. And that is basically, I think we discussed p-values. So, does anyone have any inputs or anything at all? Any comments? Any questions so far?
To be honest, like even this definition, while it makes sense, it still feels like there is something that is very abstract, like
I know,
because
right?
we talk about as least extreme as the one observed and assume
Yeah,
it is true. Like there is this huge discussion amongst the statistics people on Twitter. So I saw a thread on Twitter talking about this p value, and I think everyone is a little confused in how to make the definition more simple
Right.
and more easy to understand. So I think someone who is very new to this, I think the
It would be
definition,
confusing. I feel like
yeah,
it's just a matter of practice, I guess.
yeah, I think it makes more sense like when we read more papers and we just see
Yeah,
how it is being discussed.
right, right. So this is one of the steps of testing the hypothesis. So we have a probability statement and we have our null hypothesis and alternative hypothesis. And we are basically trying to either reject or accept the null hypothesis. Like the null hypothesis is supposed to be more important here. So based on whether we are rejecting or accepting the null hypothesis, the decision on the alternative hypothesis is also made. So, uh, this is again one of the steps. Step 4 is to compare this p value to a fixed significance level. So, we have those tables, yeah, those are critical tables for t tests, whatever they are called. So, alpha acts as a cutoff point below which we agree that an effect is statistically significant. So, like below this cutoff point, for example, if our t value is 2.34 and the alpha for that degree of freedom is 2.1 or something, so our t value exceeds this alpha. So, here it's written alpha acts as a cutoff point below which we agree that an effect is statistically significant. That is, if p value is less than equal to alpha, then we rule out the null hypothesis and agree. So basically, we consider the alternative hypothesis when p value is less than equal to alpha. But then the example that I just gave here, the p value is greater than alpha. So here we have to accept the null hypothesis and agree that no, there is no significant difference, and whatever observed result is, it is purely due to chance. So again, here's a video. This video was shared by one of our professors only. I do not really know if the audio will be okay. Could you hear this?
No, we couldn't.
Okay, I don't know how to play this on YouTube because this is just a downloaded video.
You could just directly play it on your computer, the video.
Oh, yeah, right, right.
Also, Devanshi is asking if you could share the YouTube link for the previous video.
Sure, 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 I will.
I think we can put it up on the Slack so everyone can watch later.
Right. Hold on for a moment, please. Was this alright?
You haven't played?
I did play it.
I think you'll have to first play and then share.
Okay. I feel technologically challenged.
It's not just you. The whole screen sharing and audio sharing is a trouble. Also, have you played yet?
No, I think I'm gonna stop, play it again, and then share.
Okay.
You know what? I can't really figure this one out. I'm gonna share this video. I have more or less talked about whatever is in this video, so um, I thought it
Yeah.
would have been like a summary if I could show the video.
No, that's totally fine. It's. I think it would be better if we directly put on Slack so everyone can then watch.
Right.
Yeah.
I'm gonna link all the videos.
Yeah, please, whatever you can share, do send so we can share it with everyone.